Hello, so today we are doing this problem called combination sum. So the problem says we get a set of candidate numbers, and we wanna that don't contain duplicates, and we get a target number, and the goal here is to find all unique combinations that that sum to target. And so we can choose the same number multiple times, and all numbers that we get are positive, and the solution must not contain any duplicate combinations. And for example, here we have the set of candidate numbers are 2, 3, 6, 7, and the target is 7. So we can either take just this 7 that's equal to 7, or we can take 2 times to get 4, and then add 3 to get 7, and there is no other way to obtain 7 out of this set of elements. For example, for the set of numbers that are 2, 3, 5, to get the target 8, we can take 2 4 times to get 8, or we can take 2 once and 3 2 times. So you can see we can take a number multiple times, and we can take 3 and 5 to get 8. So these are all the possible combinations. So our goal is to go from this and to return this. So we can see this problem says return all the possible configurations that out of these candidates construct target. And whenever you see a problem that says return all the possible set of things, or enumerate all the possible configurations that are constrained by something, or not even constrained, but constrained, even the backtracking should be the first thing that comes to mind. And so let's see how we can solve this using backtracking. Hello, so today we are doing this problem called combination sum. So the problem says we get a set of candidate numbers, and we wanna that don't contain duplicates, and we get a target number, and the goal here is to find all unique combinations that that sum to target. And so we can choose the same number multiple times, and all numbers that we get are positive, and the solution must not contain any duplicate combinations. And for example, here we have the set of candidate numbers are 2, 3, 6, 7, and the target is 7. So we can either take just this 7 that's equal to 7, or we can take 2 times to get 4, and then add 3 to get 7, and there is no other way to obtain 7 out of this set of elements. For example, for the set of numbers that are 2, 3, 5, to get the target 8, we can take 2 4 times to get 8, or we can take 2 once and 3 2 times. So you can see we can take a number multiple times, and we can take 3 and 5 to get 8. So these are all the possible combinations. So our goal is to go from this and to return this. So we can see this problem says return all the possible configurations that out of these candidates construct target. And whenever you see a problem that says return all the possible set of things, or enumerate all the possible configurations that are constrained by something, or not even constrained, but constrained, even the backtracking should be the first thing that comes to mind. And so let's see how we can solve this using backtracking. Okay, so I typed the same solution that we just saw on Leetcode. So checking if we have a solution, processing the solution, otherwise go through the candidates, construct them with this portion here, choose, and then backtrack, and then unchoose. You can also say that reminder minus C is the part of the choosing, right? Because we are choosing a candidate C, and so we subtract it from the reminder. But instead of doing something like this, what I do, reminder minus C and then reminder plus C, this is almost the same. I'm just passing reminder minus C to the next state, and for this state I'm not changing the reminder, right? So that's kind of the same thing. And now let's just run this and submit it and see. Okay, so this solution passes. Okay, so now let's look at the time complexity of this solution here. So first, how can we like approach this. So usually we know this is a recursive thing, right? We do DFS. And so one thing that would be useful to know in terms of time complexity, because we do this recursive call here for this backtrack function, one thing that would be useful is just to get a sense of how many times this backtracking function would be called depending on the arguments that we pass, which are the list of candidates and the target. So depending on the input, how many times will we call this recursive function, so that we can know how much stack we will be using for the space complexity, and also how much time we will be using. And so let's say, for example, here we get a target, and then we get a list of candidates. That's our input, right? So this is our input. And a couple of thoughts. So first, here we have repetitions, which is kind of, we might have 2, 3, as in the example, and the target equal to 7. And we can repeat, like we can take 2, the target equal to 7. So we might take this 2 multiple times, or this 3 multiple times. And even if we had just 1, 2, we might take it multiple times. So that kind of tells us that with repetitions, we kind of don't know, we can't like say we have to take at most the number of elements in the list of numbers, right? And so, but we have one thing we know is that the number of repetitions we take is bounded by the value of target. Why is that? Because we can take as many 2's as we want, but as soon as we have more than 7 as a sum, we stop, because that's what we do here. The remainder is when the remainder is bigger, when the remainder minus the candidate is bigger or equal to 0, we don't do the recursive call. And so at least we know that it's bounded. It's not like infinity. We don't have to take two multiple times a number that we don't know. We know that it's limited by target. And so another thing we know is that we will try to generate all combinations of n numbers that sum to, so we'll try to generate all combinations of n candidates that we have, right? That's what our function will do, that sum to some value that is less than or equal to target, because as soon as we have something that is more than target, we don't enter the loop that calls the recursive function, right? And so the number of calls, so from this we can deduce that the number of calls to the backtrack function is actually just what is just equivalent to this, right? So we will generate all combinations of n candidate that sum to less or equal to target, and that's where, when it's less than or equal to target, that's where we call backtrack again. And so all the combinations that have a sum less than or equal to this, including like the empty list, including the one that contains just 2 for the target equal to 7, but as soon as we reach 8, we don't do the recursive call. So this is equivalent to this, and this is what we are looking for the time complexity. So what we need to do is just know how much is this, the first thing. And so one thing that will help us to know is we know that we can generate an empty, we can generate 2, but one thing that will help us is if we know the maximum length, what is the maximum length of a generated combination, right? We know that we go from the empty list to up until one element, and then taking 2 elements, and then we can take repetitions, but we know that we are limited by target. So the maximum length of a generated combination is a combination that is the minimum number in the list repeated until until it becomes more than target, right? Because the minimum number will give us the maximum number of elements in a combination, right? And so that means what is the number of that element? So if we pick the min of the candidates and divide target by that, we get the maximum length array that we can generate that has a sum less than or equal to target. So let's call this value here, let's call this value p. And so what p is now, so p is just the maximum length possible for a combination of sum less than or equal to target, right? And so this is of course the ceiling, right? So this is because this value may not be an integer, a full integer. So let's just take the ceiling of this, right? And so now we have this p here that we know that we will generate from empty up until p length combinations, right? That's what we will do. So we will generate. So our function we will generate from empty length. So basically from length equal to up until length equal to p combinations. Okay, and so this here is what we are looking for to get the time complexity, to get the number of calls to backtrack. And this is easy, like, because why is that? Because the n choose k, right? This is just the combination, choosing a combination of length k out of n element. That's known. That's this, and the value of it is I think it's just the combination formula, which is just n factorial divided by k factorial multiplied by n minus k factorial. I would encourage you to look at this just videos on YouTube of that, or on Google, this formula here. And so now with this, we know that we generate from length 0 until length p, and so this here is just basically choosing first length 0, so choosing 0 out of n elements, which is 1. Of course, we can just construct only one empty list, and then taking all the 1 elements combinations, which is, for this example, it would be 2 and 3, right? And then taking all those of length 2 and keep doing this until the maximum length we can do, which is p, right? So this is how many calls to backtrack we will do, because this is how many combinations of n candidates that sum to less than or equal to target that we will do, right? And this here, it's a little bit difficult to calculate, but we know that this is less. It's bounded by cn0 plus cn1 plus cnn, because we know that p is the target divided by the min candidates, and so the min candidates would be at least since these are positive, will be at least 0, right? And so we know that at most we will do n choose n, like all the entire list, right? And now this is known, though. This here has a formula, which is that it's equal to 2 to the power of n, right? So we know now that the number of calls to backtrack, so the number of calls to backtrack is bounded by O of 2 to the power of n. It's somewhat less depending on the value of the min candidate, but at most it would be O of 2 to the power of n. So that's just the number of calls to candidates. There is another thing that is involved in our solution here, which is this sorting thing here, right? The rest is just O of 1, because we just append, pop, and then pop is a constant time operation. If we did something else like remove at an index, that may be over and increase our complexity. But here we are just doing some constant work. We are doing this for loop for the candidates, and then we are doing this sorted thing here. This sorted thing is over a ligand because that's the usual time complexity for the sorting algorithms. And we have this where we go through all candidates, but this just is the number of calls to backtrack, right, that we already computed. And so now we know that we will do this, and we will do O of 2 to the power of n. So our time complexity would be O of 2 to the power of n multiplied by n log n. Of course, it's a lot less than this because, so this is upper bound because the sorting here will do it only when we find a solution. So it's only for a subset of the number of combinations that we generate, right? But it's a little bit hard to get that tight bound. So now at least with this, we know that our upper bound is this. We can try to reduce this n log n. We can try to get rid of this. So this is our time complexity, and we can try to get rid of sorting here in our solution. So using time complexity, analyzing time complexity of this, we know that we have a problem with this sorting, that if we get rid of it, we improve our time complexity, and so we'll try to do that next. In terms of space complexity, the stack size is the number of calls to backtrack, right? So for our space complexity here, it's the path, right, plus the stack size, right? The path is just the number of combinations, right? And so our path is at most p, right, because that's the maximum length we can generate. So we kind of know that our space complexity here would be O of p plus the stack, which is the number of calls to backtrack, which at most is, so this is our upper bound though, so at most it's this, and this is of course bounded by 2 to the power of n. So this is our our space complexity. We can try to improve space complexity if we reduce the number of calls to backtrack, so we will try to do that afterwards, but yeah, so this is the analysis of the time complexity. Next we'll try to eliminate the sorting, the need for sorted function there. Okay, so now what we want to do is try to eliminate this this duplicate thing here. Basically, try to eliminate this this sorting that we are doing here. That's our goal. So how can we do that? So first, let's just see what happens if we just delete that sorted. The problem says we don't want duplicates, but and that's why we did the sorting, but let me just show you that it fails, so that we can understand what's missing in order to remove that sort. So now that we don't have sorting, let's run this and see. So you can see the problem here is that 223 is duplicate with 232, right? And 322. All these three are the same list, like contain the same numbers. It's just the ordering that is different, right? And so that's the problem that we are trying to solve. And so one way to do this is if we do something where we generate these numbers in order, so that we always do 2, 2, and then do 3, so that we do basically the first element in the list of candidates, we take it as much as we can, and then when we can't take it anymore, roll back, go to the next step, and take the next element, which is just index plus 1. Then at that point, all we will generate is 2, 2, 3, right? So let me show you here by printing what happens, right? So let's just go back to what we had before, like this, and have solution here, and print something here that says we are doing, I just have it here, so I'm just going to copy it. So we are just going to print the candidates and the call to the function, and print the call to the backtrack function, and see what happens. And so you can see, if we look at the logs here, we generated this with the reminder of 1, and then that didn't work out, so we took 2 as much time as we can, and then we took 2, 2, 3. But the problem is, when we rolled back and took 2, 3, we also took 2. And so the problem here is that at index 1, once we picked 3 at index 1, we took an element at index 0 in the candidate array. So we went back. If we do it in order, where we take index 0 as much time as we can until we can't take it anymore, then take index 1, take it as much as we can until we can't take it anymore, take index 2, we won't have this problem, because the array doesn't have duplicates. And so it doesn't have duplicate, and we sorted it at the start, then we will be guaranteed that what we will have is, if we do it in order, where we take an index as much time as we can, and then we move on to the next step, we won't have this problem of duplicate solutions, and we can just get rid of sorting, right? So that's what we are going to do here, which means what we are going to do is get rid of this sorting and this check if it exists already, and instead just add the copy. And what is going to allow us to do that is, we are going to sort the candidates here. And this is good, because this would be over log n plus whatever complexity we have before. It's no longer multiplied, right? And so whichever one is bigger, which is the 2 to the power of n is bigger, will take precedence, and so we would have just a complexity of 2 to the power of n. And so here we sort, and then we start out with an index that is just equal to 0. Basically means we take the first element as much time as we can. And so here instead, so first, this is equivalent to just taking length of candidates, right? The for loop that we had before. And instead here we will be doing candidates of I, and same thing here, same thing here. And now, instead of, since we want to take them in order, basically take the first element as much time as we can. If we can't anymore, take the next one. So we will just start out from index, so that we don't go back and retake something that we took before. And so if I run this again, you can see in the logs, so yeah, candidates.sort actually. Yep, so here we need to pass the index, which is I. Okay, so now if we look at the logs here, so we took 2, 2, and then we took 2, 2, 2. So we took the first element as much time as we can until we can't anymore, because the remainder is equal to 1, which is less than 2, so we can't take 2 anymore. We tried the next element, which is 3. So now 2, 2, 3, we found a solution. We roll back, we take the next element, which is 3 again, and we try to take 3 as much time as we can, but taking another 3 is less than 2, and so we don't enter that function. And then we try the next element, which is 3, as much time as we can again, until we hit a point where we can't take it anymore, because the remainder is smaller than 3. We go to the next element. So we can see we do them in order, and when we are taking an element 1, we never go back and take 0, and that's what's guaranteeing that we don't have duplicates. So basically, instead of just like not thinking and just generating everything and sorting, we do our generation in a way that it is in order, so that we never generate a duplicate. So this improves our complexity a lot, because as you can see, even compared to the previous solution, the number of backtrack function calls has been reduced a lot. And so with this, we end up with a time complexity that is just O of 2 to the power of n plus O of n log n, which is just O of 2 to the power of n, instead of the previous solution that was O of 2 to the power of n multiplied by n log n. Yeah, so that's it for this problem. Thanks for watching and see you next time. Bye.